We'll now continue the discussion of Fourier transform. In the last slide, we realized that for the continuous time signal, which is the red line, could be decomposed by Fourier transform into the sum of cosines in continuous time. We are now interested to repeat the problem if the signal was in discrete time. We're going to sample the signal at 50 Hertz. That means t, the sampling period, is 1 over 50 of a second. So to convert continuous time to sampled sequence of sampling period t, we replace t by nt. So all the t's here are replaced by nt, and capital T is 1 over 50, so it is n over 50. We then simplify and we throw away the capital T, which is the sampling period, to get the discrete sequence. So you realize that 2 pi 5 is 10 pi divided by 50 is pi over 5, which is 0.2 pi. So now we are really in discrete time. There's no more concept of continuous time anymore. Time is just now an index 0, 1, 2, 3. And here is capital omega, the sampled angular frequency of the dash, the big dash cosine. And in the other case, 0.4 pi is the other signal of interest. So basically, we have seen that through sampling, we can convert xt, even in the Fourier representation, into its discrete version. Later on, you'll realize that Fourier series tells us that we need to find the period first. The period of this signal, if you look carefully, is that you'll repeat every 10 samples. Every 10 samples you repeat. If you have 100 samples, that means it has repeated 10 times. Now, Fourier series says that if you have a periodic signal of 10 samples, all you need is 10 frequencies. But we can analyze using 10 samples or 100 samples. It doesn't matter how many samples we analyze it with, as long actually as it is some multiple of the fundamental period. So think of it this way. If I've given you 10 samples and I ask you to analyze it, compared to I've given you 20 samples to analyze it, since it is periodic at 10 samples, by giving you extra 10 samples, there's no new information. But it's not going to hurt as well. Okay, so what's going to change? Alright, let's see the next slide. So this is what I'm saying. Actually, if it is periodic with 10 samples, it is enough to take 10 samples and then perform Fourier series. When you take 10 samples, you are actually dividing the frequency domain into from 0 to 2 pi into 10 parts. And each of these interval is from 10 parts of 2 pi is 0.25. So you are dividing the horizontal axis of your analysis from 0 up to 2 pi in 0.2 pi intervals. That's what it means when we are looking at it in the frequency domain. By using 10 samples, you are dividing 0 to 2 pi into 10 parts. If you are using 100 samples, then you are dividing it much finer, and you are dividing it by what? It is 2 pi divided by 100 parts. So it is 0.02 pi. So basically, you realize that by using more samples, we are dividing the frequency that we can observe in the frequency domain into finer and finer parts. Now, in the next slide, we're going to see its effect. Alright, so I'm going to perform DTFS using 100 samples. That will result in dividing 0 to 2 pi in 100 parts. Each of these points in the interval here between 2 points, you can think of it as 0.02 pi, which is 2 pi divided by 100 parts. Now, the Fourier series decomposition will then generate the magnitude spectrum and the phase spectrum. In the magnitude spectrum, a high point indicates that in this frequency, there is a complex exponential. So in here, we see that there is a complex exponential at this point, at this point, at this point, and this point. So there are 4 complex exponential. This is the magnitude from 0 to 2 pi. Correspondingly, at the place where we have magnitude, we are looking at the phase. So there's also 4 phases corresponding to that 4 complex exponential. So this is the magnitude and the phase response from 0 to 2 pi. We call this the single-sided spectra. We can also look at it from the double-sided spectra, where we then actually don't look at it from 0 to 2 pi. We are looking at it from 0 to pi. And on the left-hand side, it is minus pi. So this is what we typically actually look at in a spectra, from minus pi to pi, not from 0 to 2 pi. Alright, in the double-sided spectra, of course, actually you'll realize that these 2 spectra above the pi frequency is rotated into the left-hand side. So you can believe, or you can think of it as this guy will be moved to here, and this spectra will be moved to here. Okay, so the reason being that the frequencies, or the magnitude spectrum and the phase spectrums, are periodic with 2 pi. Now, what I'm trying to share with you is the interpretation of DTFS from the signal, 100 signals, and what the DTFS will generate. How it was going to generate this, we'll explain later. But this is one of the most important information that you should retain. It is that when we perform DTFS and when we generate the spectra, how are we going to interpret it? Okay? Alright, so now the take-home message is that the 100 samples breaks the signal into frequency domain, and the magnitude and the phase spectrum will reveal what is the magnitude and the phase, corresponding phase, that is required to construct a sum of complex exponential at all these frequencies. This is the double-sided one, and this is a single-sided one from minus pi to pi. Now, why 50 minus 50 to 50? Because there are 100 points. And the interval, of course, again is 2 pi over 100 points. Alright. Now, let's zoom in. Let's zoom in into these 100 points using the single-sided spectra. The numbering is 0 to 100. But remember, 0 to 100 means 0 to 2 pi. This is k index, and this is the omega. And now, of course, if we start to count how many points in this interval, then basically this is k equals to, on this one is k equals to 10. What does k equals to 10 means? It is 2 pi over 100 times k equals to 10, and we have 20 pi divided by 100, it is 0.2 pi. So this is 0.2 pi. This is omega, the digital angular frequency. So we can find that at 0.2 pi, there's the amplitude 1. At 0.4 pi, there's the amplitude half. At 1.6 pi, there's amplitude half. And 1.8 pi, there's amplitude 1. And of course, here in the bottom is the corresponding phase. Now, what are we? Why do we have these four complex exponential with this amplitude and this phase? Let's look at the original equation representing this signal. It is 2 cosine 0.2 pi minus pi over 4. This can be represented using the Euler's equation as sum of two complex exponential, which is 1e 0.2 pi n minus phase 1e minus j 0.2 pi n minus this phase. This is an amplitude of 1 at 0.2 pi with a phase shift of minus pi over 4. What is this? Exactly this signal over here. This is 0.2 with amplitude 1. This is 0.2 omega with phase of minus 1. Okay, so minus 0.785. What is minus 0.785? It is pi over 4. There's a negative sign here, it goes below. So now you realize that this guy and this guy, this pair is actually representing this. And what about the other pair? This pair is representing this. Okay, so now you understand that actually you can think of it as the magnitude and phase spectrum as lines showing you where the important magnitude and phase are in the frequency domain. Now the last thing that you might be wondering is, this is minus 0.4 pi, this is minus 0.2 pi, but here we are talking about 1.8 pi and 1.6 pi here. This is because the magnitude and phase spectra is, what do you call that, 2 pi periodic. Okay, so this is the working to show you that 1.6 pi is the same as minus 0.4 pi. 1.8 pi is the same as minus 0.2 pi. Okay, go and read this carefully and you will see that now you understand that why we can either draw it as a single-sided spectra from 0 to 2 pi or the double-sided spectra from minus pi to pi. It's the same information. With that, we end the discussion of the DTFS interpretation. Thank you.